In this video, we will discuss binomial probability distributions. A binomial probability distribution results from a procedure that meets these four requirements. The procedure has a fixed number of trials. A trial is a single observation. The trials must be independent, meaning that the outcome of any individual trial doesn't affect the probabilities of the other trials. Each trial must have all outcomes classified into exactly two categories, commonly referred to as success and failure. The probability of a success remains the same in all trials. S and F, success and failure, denote the two possible categories of all outcomes. The probability of S equals P. P is the probability of a success. The probability of F is 1 minus P, which is Q. Q is the probability of a failure. N is the fixed number of trials. X is a specific number of successes in n trials, so X can be any whole number between 0 and n inclusive. P is the probability of success in one of the n trials. Q is the probability of failure in one of the n trials. And the probability of X is the probability of getting exactly X successes among the n trials. The word success, as used here, is arbitrary and does not necessarily represent something good. Either of the two possible categories may be called the success, S, as long as its probability is identified as P. When an adult is randomly selected with replacement, there is a 0.85 probability that this person knows what Twitter is. Suppose we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. A, does this procedure result in a binomial distribution? Yes, the procedure satisfies the requirements for a binomial distribution. The number of trials, 5, is fixed. The trials are independent because the probability of any adult knowing Twitter is not affected by results from other selected adults. Each of the 5 trials has 2 categories of outcomes. Either the person knows what Twitter is or they do not. And for each randomly selected adult, there is a 0.85 probability that this person knows what Twitter is, so the probability remains the same in all trials. B, identify the values of n, x, p, and q. N equals 5, the total number of trials. X equals 3, as we want the probability that exactly 3 of the selected adults know what Twitter is. The probability of success is P equals 0.85. The probability of failure is Q equals 1 minus P equals 0.15. When selecting a sample, as in a survey, we usually sample without replacement. Sampling without replacement results in dependent events, which violates a requirement of binomial distribution. However, we can often treat the events as if they were independent by applying the 5% guideline introduced in section 4.2. 5% guideline for cumbersome calculations. When sampling without replacement and the sample size is no more than 5% of the population, treat the selections as being independent even though they are actually dependent. The binomial probability formula. P of x, the probability of x, is equal to n factorial over n minus x factorial times x factorial times p to the x times q to the n minus x, for x equals 0, 1, 2, up to n. Where n is the number of trials, x is the number of successes among n trials, p is the probability of success in any one trial, and q is the probability of failure in any one trial. So q equals 1 minus p. The formula can also be expressed as p of x equals n choose x times p to the x times q to the n minus x, with n items identical to themselves and n minus x other items identical to themselves. The number of permutations is n choose x, which is n factorial divided by n minus x factorial times x factorial. So the two sides of this equation are interchangeable. Given that there is a 0.85 probability that a randomly selected adult knows what Twitter is, use the binomial probability formula to find the probability that when 5 adults are randomly selected, exactly 3 of them know what Twitter is. n equals 5, x equals 3, p equals 0.85, and q equals 0.15. So p of 3 is 5 factorial divided by 5 minus 3 factorial times 3 factorial minus 0.85 cubed times 0.15 to the 5 minus 3 power. That's 5 factorial over 2 factorial times 3 factorial times 0.614125 times 0.0225, which is 10 times 0.614125 times 0.0225, which is about 0.138178, and we can round that off to 0.138. The probability of getting exactly 3 adults who know Twitter among 5 randomly selected adults is 0.138. Between 1974 and 2011, there were 460 NFL football games decided in overtime, and 252 of them were won by the team that won the overtime coin toss. Is the result of 252 wins in the 460 games equivalent to random chance, or is 252 wins significantly high? We can answer that question by finding the probability of 252 wins or more in 460 games, assuming that wins and losses are equally likely. Using the notation for the binomial probabilities, we have n equals 460, p equals 0.5, and q equals 0.5, and we want to find the sum of all probabilities for each value of x from 252 to 460. The binomial probability formula is not practical here because we would have to apply it 209 times. Happily, the book shows us the stat disk display on page 204, which shows that the probability of 252 or more wins in 460 games is 0.0224 rounded, which is low, less than 0.05 rounded. It is unlikely that we would get 252 or more wins by chance. Ruling out chance, we are left with the more reasonable explanation that the team winning the overtime coin toss has a better chance of winning the game. Table A1 in Appendix A, page 683, lists binomial probabilities for select values of n and p. It cannot be used if n is greater than 8 or the probability p is not one of the 13 values included in the chart. To use the table of binomial probabilities, we must first locate n and the desired corresponding value of x. At this stage, one row of numbers should be isolated. Now align that row with the desired probability p by using the column across the top. The isolated number represents the desired probability. A very small probability, such as 0.000064, is indicated by 0 plus. Based on a poll, 60% of adults believe in the devil. Assuming that we randomly select 5 adults, use table A1 to find the probabilities indicated. The probability that exactly 3 of the 5 adults believe in the devil, we look at our table. The above excerpt from the table shows that when n equals 5 and p equals 0.6, the probability for x equals 3 is given by p of 3 equals 0.346. The probability that the number of adults who believe in the devil is at least 2. The phrase at least 2 successes means that the number of successes is 2 or 3 or 4 or 5. So the probability that at least 2 believe in the devil is the probability of 2 or 3 or 4 of 5, which is the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5, which is 0.230 plus 0.346 plus 0.259 plus 0.078, which is 0.913. In this previous section, we saw formulas for finding the mean, variance, and standard deviation from any discrete probability distribution. A binomial distribution is a particular type of discrete probability distribution, so we could use those formulas. But if we know the values of n and p, it is much easier to use the following. The mean, mu equals np. The variance, sigma squared equals npq. And the standard deviation, sigma is the square root of npq. Our range rule of thumb remains the same. Significantly low values are less than or equal to mu minus 2 sigma. Significantly high values are greater than or equal to mu plus 2 sigma, and values not significant are between mu minus 2 sigma and mu plus 2 sigma.